Hi everyone, in this video I will walk through our best performing classifier for the long default prediction task and also the three required prompts. First is that what we did to improve performance and how we assessed and improved the model fit and what we would do with more time and resources. We will also show evidence from our notebook, model comparison results, the learning curve, confusion matrix, and precision recall curve. Quick context, our target is launch status, and we focused on optimizing F1 square because it balances precision and recall and is suitable for imbalanced default outcomes. Our final model is a light GBM classifier in a pipeline with preprocessing feature engineering, five-fold stratified cross-validation, and threshold tuning. The biggest improvement came from feature engineering, meaning to better represent affordability and risk. Instead of relying only on raw variables like income or loan amount, we created derived features that align with real learning logic. For example, we applied a loan transform on income to reduce skew and stabilize patterns, and we also created loan to income to capture repayment burden. And we also created a risk interaction score since high burden and high interest rates jointly increase risk. And we also built a simple residual income proxy to represent remaining capacity after repayment. And then we added a relative income feature with home ownership groups to capture income standing among renters vs owners. These engineered features helped because default risk isn't driven by one variable in isolation. It's driven by relationships, like whether the loan is larger relative to income and whether the interest rate amplifies that burden. And then we also met the requirement to compare multiple models. We evaluated three classifiers using the same five-fold stratified key-fold CV and F1 metric. And as you can see that here, our results were logistic regression, mean F1 equals to 0.7478, and the standard deviation is 0.0041. And then for the random forest, the mean F1 equals to 0.83. And for the light GBM, is also the one we chose. The best OOF F1 score equals to 0.85, with the threshold equals to 0.61. So the story is logic regression is a strong baseline and very interpretable, but it's limited for complex nonlinear patterns and also for the random forest. It captured nonlinear narratives and improved a lot, but the boosting model like light GBM still performed best on F1 square, so we selected as the final model. And then come back to our final model. Because defaults are typically the minority class, we handled imbalance in two ways. We used the class weight balanced in light GBM, so the model pays more attention to minority class mistakes. And we didn't assume the default 0.5 probability cutoff is optimal. We tuned the decision threshold to maximize F1. On the modeling side, we also used a conservative light GBM setup, many trees, and a small learning rate for gradual learning, plus regularization and sampling to control overfitting. Specifically, we used subsampling, column sampling, and L1 divide L2 regularization, and we constrained leaf growth with mean child samples. And to assess fit and stability, we used the five-fold stratified k-fold, not a single train test split. Stratification helps because if the default rate shifts across splits, F1 can fluctuate a lot. With five folds, we get a more stable estimate. Next, we created a learning curve using F1 to check overfitting and underfitting. The training F1 stays extremely high, close to 1, and the cross-validation F1 starts around 0.18 and increases to about 0.85 as training size grows. This gap indicates overfitting. The model feeds training data very well, while generalization is lower. But we also notice the CV curve keeps improving as data increases, which suggests the model is learning real signal and hasn't completely plateaued. To reduce overfitting risk, we use regularization and sampling controls like mean child samples, subsample and column sampling, and alpha lambda regularization, so the model generalizes better rather than memorizing noise. And then for the confusion matrix. We then interpreted a confusion matrix using the OOF predictions at our chosen threshold 0.61. At the threshold, we have true negative equals to 26,949, and the false positive is 1,051, and the false negative equals to 1,306, and the true positive equals to 6,694. In loan default terms, assuming label 1 means default, false negatives are borrowers we predicted as safe, but who actually default. This is usually costly, credit losses, charge-offs, and higher portfolio risk. And then for those false positives are borrowers we predicted as default, but who would not default. That can mean rejecting good customers or pricing too high, lost revenue, and customer friction. So the confusion matrix makes the trade-off concrete and connects the metric to business outcomes. And then we comes to the recall curve. Because the dataset is imbalanced, we also plotted a precision recall curve using OOF probabilities. This curve shows the trade-off between precision and the recall at different thresholds. Our model has strong ranking power with average precision about 0.94. We also marked our chosen threshold at 0.61, which corresponds to a balanced operating point. Finally, we did a threshold search from 0.1 to 0.9 and selected the threshold that maximized our F1 score. This is how we balance risk and practical value instead of arbitrarily using 0.5. And finally, in terms of the prompt 3, with more time and resources, we would incorporate external data sources to improve accuracy and robustness. For example, macroeconomic contexts like unemployment rate or rate environment at application time, since defaults can rise during economic stress, and more granular credit bureau style variables like revolving utilization, delinquencies, numbers of open accounts, or payment history, which are usually strong predictors. And then in a real deployment, we would also implement more monitoring, track performance metrics like F1 score, precision recall, and confusion metrics over time, check probability, calibration, whether predicted probabilities align with real default rates, and run drift detection like PSI or distribution checks to see if the input data has drift. We define retaining triggers if drift becomes significant or if business metrics degrade, and would use champion challenger setup for safe model updates. So to summarize, we improved performance through the feature engineering, tested at least 3 models, handled class imbalance, and selected large GBM based on best OOFF1 square of 0.85 at threshold 0.61. We assessed model fit using 5-fold stratified CV, learning curve, confusion max, and precision recall curve, and we tuned the threshold to balance business trade-offs. And with more time, we'd bring in richer external data and build a field prediction, monitoring, and drift framework. Thanks for watching.